Why does the universe plunge into darkness at night? As day gives way to night, the cosmos unfolds before us. An infinite expanse stretches above, watching over us. This sea of darkness is interspersed with sparks of light. Among them are galaxies separated from us by billions of light years. It seems no matter how far our gaze reaches, it always finds something to observe. But if that's the case, why then is the cosmos dark? If we could look into infinity, shouldn't we ultimately see light, stars, galaxies, anything? Imagine that no matter how far light is from us, we always encounter some cosmic object. One might think the light from these distant objects would be fainter, but on the other hand, the farther we look, the more objects would fall into our field of view. This would mean that if nothing blocked this light, the night sky would be completely illuminated, and we would see the universe in all its glory. However, reality is different. Light must travel a long way to reach us. One could argue that we don't see the furthest objects because their light has not yet reached us. But why is that? 100 years ago, it was believed the universe was infinite and eternal. If that were true, light from every corner of the cosmos would have already reached us. That would mean we should be observing infinity. Yet, our view is limited. On the horizon, we only see galaxies billions of light years away, but nothing beyond. We ask ourselves, is something blocking our view? Or is there simply nothing more out there? Or perhaps the universe has its end? Maybe what we observe is just the beginning of everything, a moment before which nothing existed, and after which the entire story began, the Big Bang. When contemplating various aspects of the cosmos, we often return to the theory of the Big Bang. I myself often mention it, not dwelling too long on the details, but asking a question that naturally arises. How can we be sure? Where does our conviction that the universe began in a specific way come from? And now we are here, trying to understand the evidence of the Big Bang. In 1910, it was observed that vast spiral objects located far beyond the solar system were gradually moving away from Earth. The reason was unknown. It was also misunderstood that these objects, mistakenly referred to as nebulae, were actually not nebulae but galaxies. Spectacular collections of stars clustered around a massive center, even larger and more distant than appeared. For nearly 20 years, the explanation for why almost all these objects were fleeing further and further away eluded the greatest cosmic researchers. Sometimes the thought crosses our mind that one of the greatest challenges in science is breaking free from the thinking patterns we've become accustomed to. Some concepts are so intuitive, so natural, that we don't even consider questioning them, let alone think about them. This was the case for years with the belief that the universe was simply static. Science was immersed in the assumption that the cosmos was, generally speaking, stable, unchanging, and eternal. Every explanation had to fit this vision. The notion that the universe is expanding, now recognized as true, suggesting that space itself swells and distances objects from each other, was beyond comprehension, seeming absurd, unintuitive. It was only after 20 years that observations and calculations not only confirmed that these nebulae were galaxies moving away from us, but also unequivocally indicated that the further a galaxy is, the faster the distance between us increases. This was perfectly proportional, not random. It was known that movement doesn't arise from nowhere. There must be a cause, something that set it in motion or keeps it moving. And indeed, every galaxy might have its own history, its own direction of movement, speed, and causes for all these and such variables certainly exist. But for all of them to have the same collective motion, each must share something with the rest. A single event, process, anything that set them in motion at the same moment, in the same way. Sometimes this movement is so rapid that galaxies seem to move away from us at a speed greater than that of light, which is physically impossible. Therefore, the explanation of this phenomenon through ordinary classical movement is untenable. But if we accept that it's not the galaxies that are moving, but the space between them that is expanding, then everything suddenly makes sense. The more space, the greater the change in distance. This can be calculated, and the results match perfectly. Expansion is a certain process, and if the process progresses in an unchanging manner, we can predict what will happen in 10 billion years. Since we observe that the universe is expanding, we can assume it has been expanding before. And if we can predict forward, we can also predict backward. We see that all galaxies have the same common reason for moving away, and to find out what that reason is, we must trace this movement back. By doing so, all objects come closer and closer, until finally, we reach a point where things are as close together as physically possible, an infinitely dense point, and therein everything, the Big Bang. Of course, that's not the end. Okay, we see that objects are moving away from each other. We see that it is caused by the expansion of the universe everywhere. We can assume that since things are now further apart, they were once closer. Sure, but how much closer? How do we know that the expansion has been ongoing forever? That if we were to rewind the tape, objects would come closer and closer to the absolute limit, rather than stopping at some point earlier? This is the problem with predicting, both the future and the past. Everything is fine, as long as we assume nothing has changed or will change. Therefore, we need further evidence. But what kind of traces could such an event as the Big Bang have left? If in the past matter was closer together, we can wonder what consequences this might have had. What would such a universe look like, considering the laws of physics as we know them now? At the very beginning, when the density of everything was immense, the entire universe was like the interior of the sun. Amidst tremendous temperatures and ubiquitous chaos, particles bounced off each other. Photons were brutally directed by surrounding matter, absorbed, emitted, and absorbed again. There was an abundance of energy, but if we had been there, we would have seen nothing. The bubbling universe was too dynamic for any light to have a chance to reach anywhere. Its energy was almost immediately absorbed. With the expansion, everything cooled down until a key moment. Several 100,000 years later, the temperature dropped to a level that allowed the formation of the first atom. Protons and electrons, which previously darted aimlessly in this primordial soup, combined, and with them, billions more of their clones, forming the simplest elements like hydrogen. At this sudden moment, photons gained freedom. The universe, now slightly cleared of the previously freely roaming electrons, made space for photons. They could now traverse longer distances in the blink of an eye. Thus light was born, emanating from every place, from every corner of the universe. Photons embarked on their journey forward. If the universe is infinite, or at least sufficiently large, these photons should still be reaching us from those places far enough away that their journey could not have been completed earlier. Throughout this entire time, however, the photons would have been moving against the current, battling the flow of the expanding space, meaning not only would this journey take longer than it should have, but they also wouldn't reach us unchanged. Just as galaxies moving away from us are stretched and shifted towards the red, so too would these ancient photons have been stretched and shifted far beyond red, into a form no longer visible to the naked eye, but still detectable. The light would gradually become redder, eventually stretching into the microwave level. The intensity of this light would be constant from every direction, as at every moment we would be receiving more and more traces, remnants of the cooling Big Bang. Evidence that billions of years ago, the universe was uniformly heated, dense, and filled with energy was found in the 1960s. Cosmic microwave background radiation of negligible temperature reaches us from the entire sky, stretched exactly to the degree that would be indicated by the rate of expansion and all other puzzle pieces. Its presence is undeniable and something we must somehow explain. Every theory must take its existence into account and explain where it came from. The Big Bang theory not only allowed for such radiation, but it explicitly required it, predicting its existence. If the beginning of the universe looked as we assume, then we would have to be able to find traces of it. And eventually, we did. Of course, the question remains about these theories. Does what we've gathered unequivocally mean that the Big Bang took place, that everything happened exactly as we describe? Well, to have that 100% certainty, we would have to transport ourselves back in time and simply see it. Contrary to appearances, it's like with historical events. We can find traces that we interpret, or even chronicles describing that something happened. But someone could always come and say that there's a chance that this chronicle is fabricated or distorted. We live here and now, not in the past. So the only thing we can have are some traces that suggest to us what the past might have looked like. Traces, remnants, consequences. We observe nothing that contradicts how the Big Bang Theory describes the universe. Every piece of evidence that should be discoverable today is being discovered. As long as this is the case, the evidence supporting our belief in the theory's correctness only grows. This represents a tremendous progress compared to not so long ago when we could only speculate. The puzzle is slowly taking shape, but this is just the beginning of uncovering the history of our universe.